AP Physics, page 120, homework problem number 64. So I've got the problem worked out. I did draw a graph up here first, kind of illustrating what's going on here. We have a bow and arrow. You're pulling back the bow. I'm assuming that, okay, so this is the spot that represents you've already pulled it back all the way. We're calling that distance of 0. And then the string moves forward. As the string moves forward, it pushes the arrow forward, but as the string pushes the arrow forward, the force on the arrow gets less and less, and it's not a linear relationship. There's some complex relationship that's not given. I just drew a weird curve here to show you that the force lessens down to a 0 force after 70 centimeters, at which point the arrow leaves the bow. All right, so that would be the diagram. You didn't need to do that, but over here on the left, all right, I'm going to do the problem backwards, starting with conservation of energy, assuming there's no air friction here. The arrow goes to a height of 143.3. So if you work the problem backwards, when it gets up there, it's got a 0 velocity, and this would be the launch velocity once it leaves the string. I'm going to call that V sub I. Here it says V sub launch. So as it rises, it goes to a velocity of 0. The acceleration is negative 9.8. Total distance of height, 143.3 meters. So I just use the fourth uniform acceleration equation, V sub F squared equals V sub I squared plus 2AS, and plug the respective numbers in. The 143.3, you don't really need 4 sig figs there because I'm limiting this right now with just the 2 sig figs. I guess you could say 9.81 if you wanted to, but it doesn't really matter. To 2 sig figs, the launch speed, when you solve this, is 53 meters per second, straight up. Okay, going back over here now in this blue. Impulse is the change of momentum. It changes the momentum of something. Impulse, the equation for impulse is the average force. Here the force is not constant. There's an average force over the time period applied while it's in the bow, in the string. It tells you what time it takes to shoot the arrow, equals the change in momentum of the arrow. Well, the arrow, when it's in the string or in the bow, starts off with 0 speed. So the final momentum is the change in momentum. The final momentum when it's coming out of the bowstring is going to be the mass of the arrow, 0.025 kilograms, time the speed it comes out of the arrow, the arrow or the bow width off the arrow string, which we found out in part 1 over here, the 53 meters per second. So that is the change in momentum, which is then equal to the impulse. So if you multiply those two and divide by the 0.016, you get an average force of 83 newtons while the arrow is on the string. So in part B then, it's asking you for the impulse while it's being shot. Well, it says, what is the area under the force time curve? Well, so I sketched a new force time graph right here, and I indicated an area in green up here in the upper right. So you've had a force time, the force with time. As time goes on, the force lessens. Sorry about that bell. But bottom line, say you approximate this with a rectangle. So the area would be the base times the height. Now if you just look at the units alone, the base is in seconds, the height is in newtons, or you could do it the other way around. It's force times time. Well, force times time is impulse. Impulse units, newton seconds. So the area is the impulse. So if you just calculate the impulse, then going back down to down here at the bottom, the impulse, which is also the change in momentum, is 83, the average force, times the time, 0.016, which is 1.3 newton seconds. That's the impulse. The impulse on the arrow is the same as the impulse on the string, or on the shooter, I should say. The impulse on the two objects that are touching each other is the same impulse.